When we have replaced T1 with Y1, we can actually continue replacing A plus Y1 as well, but we will not show that. Okay, so the most important property of Tyrant's algorithm is that we will find the strongly connected components in the right order for operator strength reduction. This formulation of operator strength reduction was invented at Rice University by Keith Cooper and colleagues. So when we process a strongly connected component, we need to have a header which is the vertex with the which dominates the other. So what we want to do is to find the loop header, but we don't want to analyze the loops. Instead, we use something called reverse post order to check which vertex must be the loop header. We will come to that in a moment. Anyway, when we have found a strongly connected component, then we check if it has a single member and if it has the proper form, and then we replace it as we did for the multiplication. And if not, we say that the header of this node in the strongly connected component is bottom, or a null pointer. Otherwise, if there are multiple members, then we classify this to see if it's an induction variable. So, which are the valid forms? Well, it's this. So, induction variable times region constant and some variance of that. Here, region constant means that it's not modified within the loop. So it does not have to be a real constant. It's sufficient that it's not modified if it's a variable. So region constant, either it's a constant or the vertex which which defines this strictly dominates the header for the strongly connected component. So here A and B are region constants. The reverse post order is computed using depth first search, and the one with the least is the start. Okay, and we can use this to determine which vertex in a strongly connected component is the header. And you can think of that as the loop header. I mean the root node which dominates all other nodes in a loop. Okay, so we do that first, and then we check if this strongly connected component has an operator which is none of this, in which case it's not an induction variable. Okay, and then we check the operands if it was in this set, and see if it's defined either in the strongly connected component, or if it's not, defined outside the strongly connected component, or if it's not a region constant, in which case it's not an induction variable as well. Okay, so if we concluded that this strongly connected component describes an induction variable, then we set the header that we found as an attribute of each node in this strongly connected component. And then we go through every instruction in it and see if we can replace that operation with a simpler one. Now we come to the pseudocode for actually traversing the strongly connected component that we want to copy and replace with a simpler operation. This is in principle not very complicated, but what we have to do is to avoid recursing forever. So we check if we have already replaced a certain operation. Anyway, we start with an induction variable, a region constant, and an operation. And then we find an expression for this recursively. Replace it and say that this new operation has the header of the induction variable. So they reduce. Then we look up if we have already computed this. And if we have not, we create a temporary and compute. And then we recursively do this by, what we do is to copy the strongly connected component by following the operands. And eventually we have copied everything. Implementing this algorithm is one example of an extended project that you can do in order to increment your grade by one step from a 3 to a 4 or 4 to a 5. We will not go through this and in detail because it's quite messy, but the general idea from this, and this is very simple, namely to copy this. Okay. For the oral exam, I will not ask you to explain the details of these three functions.